Next, let's introduce the idea of thermohaline circulation. Now, don't get intimidated by the long name. Write in your notes that thermo means heat, which you probably already know, and that haline refers to the density of the water. So that thermohaline circulation refers to the global ocean circulation that is driven by differences in the density of the seawater, and that density of the water is controlled by two things: temperature and salinity. Now remember that salinity is the amount of salt or dissolved minerals in the ocean water. So this thermohaline circulation is different depending on the concentration and the temperature of the water. So make sure you get that in your notes. Also write in your notes that the global ocean circulation system, often referred to as the ocean conveyor, like you see here right now, transports heat throughout the planet. Now in this diagram, the white sections represent warm surface currents. So here are the warm surface currents now by this white ribbon, while the purple sections represent deep cold currents. So here are the deep cold currents right here. So this is called thermohaline circulation. And this has everything to do with the wind structure on the Earth. And we'll talk about those wind structures here shortly in a few slides. Okay, now let's move on to upwelling and downdwelling, things we mentioned earlier in the podcast. Write in your notes that upwelling is the movement of deep water to the surface, and that this process moves cold, nutrient-rich water to the surface, which is responsible for producing abundant marine life. Next, write that downdwelling is the movement of warmer, nutrient-depleted surface water downward and is not associated with high productiveness or abundant marine life. So, let's think about this now. That surface water, which is exposed to the sun, has a bunch of organisms and plants in it, and eventually that surface water gets depleted. The oxygen gets used out of it. It starts to fill up with carbon dioxide, starts to fill up with waste products of all the organisms that are on the surface of the ocean. So what needs to happen now is we need to get that nutrient-rich water that's underneath or deep up to the surface. Well, the process that does that is the cycling between upwelling and downwelling. So let's get that in your notes. Upwelling and downwelling recycle nutrient-rich water with nutrient-poor water. Also write that the nutrient-poor water moves from the surface to the depths, and the nutrient-rich cold water moves from the depths back up to the surface now, so those organisms can use it. Okay, now just a brief mention of something you studied when you were in junior high called the Coriolis Effect. The reason we're going to mention it is because it has a tremendous amount to do with the way the wind is circulated and the way the atmosphere is circulated on our planet. Now, get in your notes that the Earth's rotation causes anything that moves long distances, such as prevailing winds, to appear to change direction, and that the apparent change in direction of a moving object in a rotating system is called the Coriolis Effect. So this is due to the Earth's rotation. Also get in your notes that this effect is evident on the Earth because in the northern hemisphere, that's where we live, and you see now a picture of the northern hemisphere. You see the Earth now rotating on its axis. And now let's talk about the northern hemisphere first. In the northern hemisphere, as the Earth rotates eastward, you should be writing this down, an object traveling from north to south will appear to move to the right. So you see that here. So as an object is moving from north to south, because of this Earth's rotation, it's going to look like it's moving this way. Now, in the south, in the southern hemisphere, it's just the opposite. As we're moving now south, objects deflect to the left in the southern hemisphere. So to the right in the northern hemisphere, to the left in the southern hemisphere. Now, also write that the Coriolis effect is more predominant closer to the poles. So the closer you get to the poles on the Earth, North and South Pole, the more exaggerated the Coriolis effect is. Now, just as a side note, and I'll ask you about this on the quiz, pilots have to take this into consideration, particularly if they're flying from north to south. So if they're flying now from north to south, they actually have to take the Earth's rotation into consideration. So if by chance they're flying from this point right here to this point right here, well, if they don't fly this way, then that point's now going to be way over here when they get there. So when they flight plan, pilots have to submit a flight plan that takes the Coriolis effect into their flight plan so that they get where they need to be because of this rotation effect. So that's the Coriolis effect. Now let's move on to global air circulation and how it's affected by the Coriolis effect. Write in your notes that because it's warmer, air rises at the equator and then falls at the poles because it loses heat and becomes more dense. However, instead of creating one giant circuit from equator to pole, there are actually 4 circuits all affected by the Coriolis effect. So let's get those circuits in your notes and a brief description of each. And you'll see them now represented here on this diagram that I've given you. This has a bunch of stuff in it: polar cell, Ferrel cell, horse latitudes. We're not going to really worry about that. We're going to worry about things like the westerlies and the trade winds, etc., etc. So let's write those down in your notes and get now a description of each. First are the southeast trade winds. Those are right here. The southeast trade winds. Now the southeast trade winds occur just south of the equator, so you're writing this down, and move east to west. So the southeast trade winds occur just south of the equator and move east to west. Next now are the polar easterlies. You see those right here. The polar easterlies. The polar easterlies occur between 60 degrees latitude and the poles. So here's 60, and here's the poles. So the polar easterlies occur 60 degrees and up. And then these winds move east to west. So the polar easterlies move east to west. So make sure you get the location and the direction in your notes. Okay, next are the mid-latitude westerlies. Here are the westerlies right here. There's one here, and there's one here in the southern hemisphere. The mid-latitude westerlies. Those occur between 30 and 60 degrees latitude. So right here, between 30 and 60. 30 and 60. And move from west to east. Okay? That's why they're called the westerlies. They move from west to east. So again, I want you to know where they occur between 30 and 60 degrees, north and south latitude, and these move from west to east. So get that in your notes. And then finally we have the northeast trade winds. You see the trade winds here? The northeast trade winds, which occur just north of the equator and move east to west. And then the southeast trade winds, which occur south of the equator and move east to west. What we mean by south of the equator is from 0 to 30 degrees. So get that in your notes. So 0 to 30 degrees, northeast trade winds move now east to west. So make sure you get the description and the location of each of these circulation patterns in your notes. Okay, now let's look at how these currents can affect the climate of the Earth. First, write in your notes that ocean currents cause a phenomenon called the El Nino Southern Oscillation. The El Nino Southern Oscillation, also referred to as ENSO. So meteorologists refer to the El Nino Southern Oscillation as ENSO. Get that in your notes, because we're going to kind of shorten it up and talk about ENSO instead of El Nino Southern Oscillation. Now, write in your notes that La Nina is sometimes referred to as the cold phase of the ENSO. So La Nina is the cold phase of the El Nino oscillation, and El Nino is the warm phase of the ENSO. And also write that these changes in normal surface temperatures can have a large-scale impact not only on ocean processes, but also on our weather and climate. So La Nina and El Nino. Now, also write in your notes that El Nino and La Nina episodes typically last from 9 to 12 months. But some prolonged events may last for years, and they often begin to form between June and August, and they reach their peak between December and April. Then lastly, make sure you write that they start to disappear, their effects start to disappear between May and July of the following year. So again, they last 9 months, some can last for years, they form between June and August, and they disappear between May and July. Now, how often these phenomena show up can be quite irregular. However, write in your notes that El Nino and La Nina events occur about every 3 to 5 years. And typically, El Nino occurs more frequently than La Nina. Okay, so let's look at El Nino first. You see that right here in this diagram. Write in your notes that El Nino means the little boy or Christ child in Spanish, and was originally recognized by fishermen off the coast of South America in the 1600s. Now, they noticed the appearance of unusually warm weather in the Pacific Ocean. Also write that that name was chosen based on the time of the year, around December, during which these warm water events tended to occur. Also write that ENSO, or the El Nino Southern Oscillation, refers to the cycle of warm and cold temperatures as measured by sea surface temperatures of the tropical central and eastern Pacific Ocean. Also get in your notes that El Nino is associated with a band of warm ocean water that develops in the central and east central Pacific Ocean around the equator. Now, this includes the Pacific coast of South America and occurs again around December. So you see now in this picture, in a normal year, this cold water along the South American coast is pushed this way, westward, in a normal year. And because it's pushed westward, all this water is pushed this way, it leaves cold water now next to the South America and North American coastline. Now, in that situation, you get a large pool of warm water gathering around Australia way west. And because of that, we get colder weather in the winter. So, for example, this winter is a typical normal year. So this warm water gets pushed out of the way, and winter now starts to come down from the north. Now, in an El Nino year, you see now that the currents move that warm water in the opposite direction. Because that warm water's moved in the opposite direction, it now is able to warm up the water near the coast. And because it warms up the water near the coast, our winters now are fairly mild. We haven't had a mild winter in a while, but it would cause now a milder winter. So when this pocket of warm water gets moved this way, we have what's called an El Nino winter. And our winters would be much milder. So what I want you to write in your notes is that during a normal wind situation from the equator, these winds gather warm water and move it towards the west, away from the U.S., which leaves colder water along our coast. The end result is a normal winter, like we're having this year. However, write that in an El Nino year, those same easterly winds are much weaker, which allows that warm water to slowly move eastward, again towards our coast, which can then cause parts of the U.S. to have a much warmer, milder winter. Okay, I know I went over a little bit. I'm at 1624. So take a picture of these notes, submit them to Moodle, grab that study guide, answer the questions, and I'll see you next in part 3 of our discussion of oceans. Bye.